All right, so we're going to continue on with the time stepping scheme ideas. So, in fact, I guess it's really time and space stepping schemes. And now, kind of in some sense, I'm going to step back a little bit into the more traditional way of thinking of this stuff, which is just discretization in time and space. There's been specialty algorithms that we've developed, so far in the class, which is just write it down as a system of ODEs, and you throw it into like ODE 4.5 or 2.3 or something like this. But it's sort of, in some sense, is a more generic way to think about it. And the real advantage to thinking about the ways we're going to talk about is because it gives you some analytic insight, especially concerning stability. Remember, you're making an iteration scheme for this thing in the end. And what you really want to understand is this iteration scheme stable. Does it go to the right solution? So that's one of the most important things to do. And so we're going to consider some really easy equations, because in the end, for stability, you can only say something about stability for really easy equations. But it gives us some insight to what are the things you have to be thinking about. This is actually part of the problem with computations, which is we're going to develop all this theory about, we're going to lay down some ideas for how to do discretization, talk about stability, and in the end, we're doing it for equations that look like this, for instance, which I can solve by hand in the first place. So there's a limited validity to it, but it gives us a way of thinking about how to characterize stability, brings up some important issues, and then when we go to harder problems where we don't have analysis available, some of the ideas, though, we learn from here, the cartoons carry over, as it were. Okay? All right, so this is the equation we're going to consider. One-way wave equation. Easy to write down a solution to this, but we'll talk about solving it numerically. So far, what we've done is we've said, okay, let's discretize this thing. Particularly, I have a space derivative here. So you could discretize by basically saying, let's use our finite central differencing method for getting what the derivative is. Now, this is just a slope, right? Rise over run. So when you discretize, what you end up with is the following. Where u of n is it's u at some t n x of n. So this is all the ODEs that you have. Now what we've talked about so far doing is just say, well, I can just throw that in ODE 4.5 right now. Then you're done. Big system of ODEs. But let's be a little bit more careful about what we want to do now, which is we've discretized space. Now let's just discretize time as well. In particular, this is just a time derivative. Well, there's no difference really in discretizing space or time. In other words, I could use a slope formula for calculating this derivative as well. Okay? So what I'm going to do is say, let's let u of n m be basically u at time t of m, x of n. Okay, so the m up top is going to refer to time, not a power. That's why I've put it in parentheses. Okay? And so what happens is, now let's discretize this thing here. Let's say, okay, I'm going to use a slope formula, a rise over run, which looks like this. That's my approximation to the slope. That is one hell of a breakfast. Is that a Twinkie or Ding Dong? That's awesome. I thought you were supposed to have like a croissant or something, but no. You've gotten to the American way. What is that? Zingers. Zingers for breakfast. Man. You rock. You just, I think more highly of you now. Okay. Okay. Yeah. So, anyway, this is just a rise over run formula for the time. And it says a time, the solution at time m plus 1 minus time m divided by delta t, because that's the spacing between, is equal to, well, that's what we approximate here, is equal to this over here, which is c u of m plus 1 minus u of m n minus 1 all over 2 delta x. The thing we can do now is solve for what? The idea is that what we know is a certain time m, we know the solution, let's say. Then this gives us an algorithm for getting the solution at time m plus 1. In particular, you get the following. U of n, m plus 1 is equal to u of n, m plus lambda over 2, u of m, m plus 1 minus u of n minus 1, m. Where lambda is equal to so here's our algorithm. This is our iteration routine. My solution in the future is what it is right now plus this contribution here. So it's a lot like our ODE stepping techniques, but now we've just written down the iteration itself. And the important thing is to just have this lambda over 2 in front of this thing here, where lambda over 2 has the characteristic delta t, delta x. This lambda is called the CFL number, after Courant, Friedrichs, and Levy. It's a very important parameter. In fact, if nothing else, you should understand that the CFL says something fundamental about the problem. Most iteration schemes that you develop, the stability of that scheme will depend upon what the CFL number is. Some of these iteration schemes will only converge for lambda being small enough. In fact, at the end of the lecture, I'm going to put up a little table and tell you, for the different schemes we developed today, what lambda has to be for these schemes to work. Now, given that, you could ask the following question. You see that, in fact, delta t and delta x are completely wrapped up in each other. In other words, you can say, I want to double my spatial resolution. If you ask that question, you're saying, I'm going to cut delta x in half. What did you just do to lambda then? You doubled its size. Now remember, this has to be smaller than a certain value. You just doubled it by cutting it in half. So if you want to control this lambda, suppose you're right at the edge of where stability is to run this thing, and if you just increase your resolution by double, you have to cut your time step in half too. These are not independent actions. In other words, you can't say, I'll just run with a delta t like this, but play around with my delta x. You play with your delta x, you've got to play with your delta t accordingly. Okay? Very important what happens with this parameter. So it's the thing that really controls all the stability. And the idea, again, is you fix your CFL. For a given scheme, often you know what the CFL stability criteria is. You run it, and you have to maintain this. Okay? Notice, though, however, if you want to take smaller steps in time, you can actually then go with less resolution in space. So that's one thing. But if you want to go with better resolution in space, you always have to decrease your time. Okay? So if you're solving a problem, you want better resolution, you want to double your resolution, you've automatically guaranteed yourself 4 times the amount of running time, right? Because you have to double, you have to cut that in half as well. So not only do you have twice as many points to calculate, but you also have to run it twice as long, because your delta t is going to be half the size. Okay? So every time you mess around with stuff like this, your computational time goes up. All right. So notice, by the way, that this algorithm, so this is time m plus 1, time m. Basically, if you want to update your solution in the future, what you need to do, if you want to update your solution at u of n, m plus 1, in other words, my solution at point n, m plus 1 is the future, basically uses how many points? 3 different points at time m. Uses these 3 points, which help update to the future solution. So it's a method of lines. Here's your line of solutions. You update the next line. How many points are involved? 4. So this creates what's called a 4-point stencil for updating your solution. Okay? Because there's 4 points involved. That's what you get. Okay? Now, let's come back over here for a minute. Notice what we've done differently here. We've treated time and space differently. We've treated space with center differencing. No, this is a slope. So when you calculate derivatives, that's a slope, that's a slope. One's in time, one's in space. Big deal. This doesn't really count. Here, when you do the space one, we use center difference. Remember, when we did the time one, however, we used not center difference. It actually was a forward difference. It uses current point plus a time in the future, delta t. So it's using a different slope formula. Why couldn't I use the same slope formula for both? Center difference in time, center difference in space. Well, you can. It's going to change things a little bit. So in fact, going from here to here, let's now use center difference in time here and see what happens. When you use center difference in time for your time derivative, you get the following. This is your center difference in time. You use a point in front and a point behind. So now you're trying to calculate the future point, and you're calculating this with using a point in the past. Plus, on the other side of the equation, you still have over there c over 2 delta x, u of n plus 1m minus u of n minus 1m. Okay? So again, if we want to write this as an algorithm for predicting the future, you would rearrange this to be the following. U of n, m plus 1 is equal to u of n, m minus 1 plus lambda, u of n plus 1, m minus n minus 1, m. Now, this is almost exactly what we had before. Lambda is still the CFL number, exactly as we had it before. The only difference is this. Here, before we had u of n evaluated at time m, not time m minus 1. This is using not the current time, but one time in the past. And there was a lambda over 2 over here. So this is what's called Leapfrog method 2-2. And here's why. Basically, you've set up a procedure. If we think about a stencil again for predicting in the future, this stencil for getting a future point right here, call this u of n, m plus 1, what does it rely on? It relies on the point n at m minus 1. So not the current time, but one in the past. Then the current time with 2 points on the side. So here and here. So it's a different stencil. Still a 4-point stencil. But notice, when you update your future, essentially this leapfrogs over to here. So all these points give you a new solution. And then when you go to the next point, you need this point to give you the solution here. See, so you're leapfrogging. It's just like the game. Okay? So Leapfrog 2-2. The 2-2 stands for second order accurate in space, second order accurate in time. Remember, we use second order central differencing for both. Okay? All right. So that's why it's called Leapfrog. What are the drawbacks? What are the advantages? So one of the questions you could automatically ask is, why would I do this? Because there's a huge drawback to this, which is when I do this, the other method I had before, which is given by here, when I just used basically Euler stepping in the future, I simply took this whole line, updated the next, this whole line, updated the next. If I give you one initial condition, from that point on, I can just run this up. Here, this is not self-starting. If I give you one initial condition, that's not enough to get this thing going. Why? Because I need 2 layers of time, 2 lines of time, in order to generate a third line. Okay? So it's a little bit tougher. So you need some way to start this algorithm off. So what you typically would do, you maybe start it off with the one-stepping scheme, just generate 1 point, and then now you have 2 lines. Then from there, then you switch over to this algorithm, and you can alternate back and forth to go up into the future. Why would you use these 2 different schemes? Well, it turns out this is stable. This is not. But when I say that, you got to be careful, because this is not stable for this specific equation, ut equals cux. In particular, usually the Euler schemes, such as this one here, are not stable if you're doing wave-type equations. Whereas, if you're doing heat equations, these work great. So in other words, if you were to develop a scheme like this for that equation, works great. No problems. But for that equation, blows up. We're going to talk about the stability of these in the next couple lectures, why that is. So the scheme you pick is very important. Leapfrog, however, Leapfrog is very stable for wave propagation equations. It's unstable for heat equations. So depending upon what kind of equation you have, you don't use that one or this one. Okay? And the stability is all dependent upon lambda, what you choose lambda to be. I might as well give out some of these results now instead of hiding them for the very end. In particular, Leapfrog 2.2. Here's the stability. It's stable for lambda less than or equal to 1. It's the biggest value you could take lambda to be and get this thing to work. Okay? Now, one thing that's important. When you solve these problems, you would like to take as large a delta x and as large a delta t as possible, right? Because that's going to make the code go as fast as possible. So typically you're trying to make it as big as possible, yet stay within this constraint. We'll do some programming. Probably not next lecture, but the lecture after. We'll actually throw in these algorithms and you see what happens when you violate this. Bad things, okay? All right. And for this one here, by the way, for this specific problem, never stable for any value of lambda. Okay? All right. Let me find out where I was in my notes. Wasn't there. Oh, see, because I flipped ahead to my little table, I've lost myself. But there, I'm finding it again. Okay, here we are. Now, since we're going to jettison this method, right, because it's unstable, we could say, okay, this is unstable. This one works nicely. Suppose I want to improve accuracy. One thing you can do to improve accuracy is to say, well, I could take smaller delta x's, right? Because that will give me a better accuracy. Another thing to do, which is a smarter thing to do, is to use an improved accuracy for the derivative. Now, if you go back to lecture number 2, I give you central difference formulas that are order delta x to the 4th accurate. Here, this is order delta x squared accurate. So you could easily just use that. So for your same delta x you use here, which is, you say 0.1, your accuracy would be like 10 minus 0.1 squared. So it's like 10 to minus 2. Well, if I use this 4th order accurate scheme, for differentiation. I can still use 0.1, and I get accurate down to 10 to the minus 4. So quite an improvement. So how would you do something like this? Well, you would do basically the same thing as you have here. You would discretize this equation as you had before. You say, okay, now let's just do center differencing in time again, because that seems to give me stable results. And now for the derivative ux, let's do fourth order central differencing. Okay, so if you central difference in time, you find u of n, m plus 1, minus u of n, m minus 1, and it's a 1 in there. It's equal to c times u of x. Well, if you remember the formula I gave in class, you basically get minus u, m plus 2, m, plus 8, u of n plus 1, m, minus 8, u of n minus 1, m, and then plus u of n minus 2, m, all over 12 delta x. That's your scheme, and what you end up with then, if you solve for your future time, is the following. U of n, m plus 1 is equal to u of n, m minus 1, so it's still a leapfrog, because the point in the future depends not on the point right now, but one point in the past, plus lambda, which is your CFL, 4/3 u of n plus 1, m, minus u of n minus 1, m, minus 1/6, n plus 2, m, minus u of n minus 2, m. This is called Leapfrog 2.4. And you can imagine having a Leapfrog 2.6, Leapfrog 2.8, and on and on and on. Usually you don't do more than Leapfrog 2 here. Why? Because if you did a Leapfrog 4 in time, you would need how many slices in time? You'd need, what it would be saying is, to get my solution 2 points in the future, I need 2 points in the future, the point in the future, current time, and 2 points in the past, which is kind of stupid because, I mean, you don't even know what the future point is, let alone 2 future points from now. Okay, so it's kind of a harder one. But Leapfrog 2.4 now, if you look at its stencil in time, if I want to update a point in the future, I need the point 1 in the past. So here's your current point, here's your future point, and here's your past point. So this is your past point, and then 4 points. Six-point stencil now with your iteration method. These 5 points come together to give you the value for this 5 points. Again, not self-starting, but great improved accuracy. Okay, so part of what this lecture is also supposed to show, which may or may not be clear, is that there's a large variety of schemes you could come up with. Leapfrogs are some of the more famous ones. Yeah, Pierre.
Okay, what you're saying is like you have, for the initial condition, you know what it looks like in space at t equals 0.
Yeah.
And then you say, I can find out what it would look like at t equals 1, 2, 3, 4.
Yeah.
We could imagine that since like how the derivatives are, we could know how one point is moving and find out how the rest of the space would be moving in time, right? So starting with
starting with initial value for all time in x.
Yeah, vertically. So you would just like rotate your drawing by 90 degrees, right? And it would be possible, right?
Yeah, yeah. And for wave equations, this makes sense. So Pierre's question really relates to, suppose you know at a specific point in time. In fact, oftentimes, if you know what happens at a boundary, and you know how it behaves for all of time, what you know is that boundary will generate waves. So you could think about that as being somehow rotate it, think of x as being t and t as x, and watch what happens with what comes off that boundary. That's your initial condition, which propagates out then into the rest of the domain. The only problem with that is you'd have to assume that nothing's being generated from somewhere else. So if you had a boundary over here generating some stuff, if there was another one over here, you'd have to know about it, because this would also be generating waves. So that's the only problem with that.
So that would be the equivalent of having boundaries in time. For example, having knowing the profile at t equals 0 and be like, I want to end up at t equal 20
right.
at this thing. That would be the equivalent, right?
Yeah, right. Yeah.
Okay.
Okay. So the idea is that there's a lot of variety for things you can do for schemes. Okay? And mostly what I wanted to present through this course of these different types of schemes is some of what I would say are the most famous. Leapfrogs are really very heavily used, specifically in electromagnetic wave propagation. They're really good for wave propagation problems, and people use these stencils all the time for doing the wave propagation problems. So being aware of what a leapfrog scheme is pretty important. If you've taken a computational class, you should at least have an idea of what that means. Okay? A couple more that we can start thinking about. Okay. I'm going to erase this stuff. Anybody have any questions more? Good. So now the one that we want to talk about is just, oh, by the way, for Leapfrog 2.4, I should have thrown out there before I erased it, was that it was stable for lambda values being below about 0.7. Okay? So as long as your CFL is below 0.7, 707, then it's stable. Another one I want to talk about is what's called Lax-Wendroff. And in some sense, this is just really a clever trick. But it's really nice because it gives you a really nice way to think about this problem, which is think about just at t plus delta t. Now, without doing anything with discretization, I just want to do a Taylor expansion of this thing around t. So let's do it. Well, if I expand around time t, I get u of xt plus delta t du dt at xt plus delta t squared over 2 factorial let's ignore the higher order terms. Okay, that's just a Taylor expansion. I haven't done anything fancy. What is the equation we're trying to solve? The equation you're trying to solve is that ut is equal to c ux. Hey, there's a ut right there. What is that supposed to be? Ut is supposed to be cux, so think about that being cux, right? I'm just using what my equation is. What about this? 2 derivatives. What do I do with that? Well, check out this equation. Take a time derivative of the whole equation, both sides. What do you get? utt is equal to c uxt. Well, differentiation, partial differentiation can be interchanged. What's ut? Oh, is that cux? Indeed it is. Okay. Everybody agree with that? So, oh, well, I can put that up here. Isn't that just c squared uxx? Now notice what this essentially does. Just by using this observation, number 1 and 2 here, you plug those in there, and what do you have? You have an iteration scheme. In particular, you have your time in the future, u of n m plus 1 is equal to your current solution plus delta t times c ux. Well, ux is, you can use your central difference formula there for the derivative. Right? Point in front, point behind in space, divided by 2 delta x. You already have your delta t out here, and you have the c to make up your CFL number. So that one gives you this. U of m plus 1 minus u of n minus 1. And then the last piece is this thing here, which is delta t squared. This is c squared uxx. Well, the c squared comes out to the delta t squared. The uxx, we can use a central difference formula for the second derivative, which is minus the point in front minus 2, the current point, plus the point behind, divided by delta x squared, if you look at the central difference formula. And so this is going to give you lambda squared over 2 u of n plus 1 m minus 2 u of n m plus u of n minus 1 m. And there is the Lax-Wendroff scheme. Very clever use. Now here's the interesting thing about it. What it says is, it's again a 4-point stencil, because now it relies on, the current point and its neighbors and the current time to get the future time. Without this term, this is the big addition here. If you just take this term out, what do you have? You have the Euler method that we talked about first. That's unstable for all lambda values. But by including this correction here, it adds a little bit of what's called numerical diffusion. You're adding a diffusion term over here, and this thing here basically helps stabilize the thing. So for the heat equation, Lax-Wendroff is not a bad scheme to use. Okay? So you've added this term here, which helps stabilize what was previously always unstable for any lambda values. Okay? So you can see this is just a clever trick, and it works great for this equation. Okay? And there's all kinds of tricks like that for different equations out there. So if you have an equation that's your favorite to solve, chances are, somewhere in the literature, someone's come up with a really cool trick that if you have constant coefficients, for instance, in this problem, boom, out pops this. Here's a really nice scheme for solving it. Maybe it has some nice numerical stability properties. And Lax-Wendroff usually does. Okay? And mostly what I propose this for is that not only is Lax-Wendroff sort of a standard scheme that people throw out there, if you look at most numerical books, they'll have Lax-Wendroff in there. So you should be aware of what it is. But also it shows you the clever use of Taylor expansions and using just information about your equation to get out a pretty reasonable scheme. Not that much harder than it was before, but there you have it. So a lot of people have done a lot of research over a lot of time to develop these different kinds of schemes. Okay. One other scheme I want to talk about. Go back to the simple equation again. Notice what we've done. We've made one major assumption here, that if you weren't paying attention, or even if you were, you probably would. I just passed it off without even having to think about it. Think about when we discretized this. We discretized time, and we discretized space. Let's do it again. Discretize my time. We're going to go back to what we did before, which is Euler. Let's use a slope formula in time, which just says u of m plus 1 minus u of m all over delta t. There's my slope formula. I did that before. That was my Euler. But here's the difference. Central difference this. Here. Well, what was it? That was just, well, that's fine. Now before I just said at time m. This is what we had before. Why does this have to be time m? There's nothing in this problem that says there's something special about the current time. The reason we did it before is because I know what the value is at time m. Why can't I just do this? We'll evaluate the spatial derivative at the future. Now, partly you kind of go, that's kind of a dumb idea. I don't know what the future is. That the whole point of this iteration scheme is to get the future point. But notice what happens when you do this. When you do this, you can write down then the following equation. Here's your iteration scheme with lambda in it. Like that. Get the future point in terms of the current point plus some future points. So you kind of think that's dumb, but really, if you look at this thing, this is nothing more than a big matrix system where I can solve for my future point. In particular, you can write this as an ax equal to b, which takes the following form. Where a okay, let me see, negative lambdas on the off diagonal. It's something like this. This is what we find if you try to solve this. So if I want to get my future point, what I've actually got to do to solve this set of equations is solve an ax equal to b problem. Now, you the thing you can easily ask is, wait a minute, isn't that expensive to solve an ax equal to b? We've spent a lot of time talking about how long it takes to calculate this. In all the other schemes we've talked about so far that we've been developing, it's just an iteration. You're not solving anything. You're just putting it in a loop. Here, every time I go forward, I've got to solve this problem. I have to pay a price for this. Now, why would that be advantageous in any manner or any way? The only thing that's advantageous about this, the only way this can really even make it into a non-laughable scheme is if somehow, in doing this, the stability properties are so great that it's worth solving this every single time. And in particular, this method is called an implicit scheme. Okay, and it's the backward Euler, because now we're using the forward points instead. And this implicit scheme, basically, when is this scheme stable? This is why the scheme sticks around. Any lambda you pick, any say CFL condition, it will be stable. Remember, we've put restrictions in everything else so far. We said leapfrog as long as lambda is less than 1. Leapfrog 2.4 as long as it's less than 0.7. The Euler was just unstable for any lambda. Here, you take any lambda you want, this scheme is stable. Not necessarily accurate. Okay? Remember, there's two issues, stability and accuracy. But the point is, I could take this thing and I could just run it, and I know that it's not unstable. It's not an unstable iteration scheme. I still have to pick my delta t and delta x in such a way that I get the accuracy I would like, right? But for the most part, boom. This is the big win. This is why people would pay the price of solving this equation every single step. Yeah.
The second line, you for the time variable, you evaluate this at second line up, yeah. This one, you're saying we're using a center differential. Like
So this is a forward difference.
Forward difference for to evaluate the point at time m, right?
Yeah. So okay, so here I'm trying to take a slope in time. Yeah. So I need two points in time. So I'll take the current point and a future point.
To determine the current.
No, just to determine the slope, right?
Oh,
So this is just a slope formula right there. This is a slope, rise over run. And I'm just going to use current point, future point to determine what my slope is. And over here, I'm taking a slope in space, but I'm going to evaluate this slope in space at time m plus 1, not time m. And that's the big difference. If you evaluate this time m, it becomes the Euler scheme, which is always unstable. If you evaluate m plus 1, it's this scheme here, which you have to solve this. It's stable for any values of lambda. So there's a huge contrast in stability properties.
But you're looking to evaluate the m plus 1 point, right?
Right. You're always looking to evaluate the m plus 1 point. That's the one you don't know. You know all the m points. So that's when you put it here. This is your matrix A, you know all the m points here. So all you have to do is do a backslash command to get that.
And A is going to always be the same anyway.
Yeah, so you
take
do-
LU, take
That's right, you do an LU on it. The only problem with this, if you try to do something like this for a nonlinear problem, this becomes a nonlinear system of equation solve. It's kind of painful. So, here's the idea. These implicit schemes are incredible in the sense of results like this. That's unbeatable. I mean, that's amazing. This is what you really want for stability. Is there any way I can somehow tap into the power of this implicit scheme without having to do this? And there is. And these are called the predictor-corrector methods. So if you go back to lecture 1, we talked a little bit about them there, but in the PDE literature, they're called McCormick schemes. Now, McCormick schemes, basically, what they do is say, look, what is the big problem with this here? The big problem with this is that I'm trying to update my future. What I'd really like to do is iteration procedure where I take my future points, the current point, plus something. But I don't want this something to be my future points I'm trying to solve for. So why don't I, instead of using the actual future points, why don't I use some kind of predicted future points? Like, what should the future points sort of be? Well, one thing you could do is say, let's predict the future. Okay? And if you can predict the future well, you could predict the Super Bowl and make lots of money. And here we're just predicting what this scheme will do. No money involved. Just a lot of work. This is not what you want to be good at predicting. There you go. This is the Euler method. It says my point in the future is the current point, CFL, plus the x derivative spatially and evaluated m. Now what we do know about this method is this is unstable. What that means, if you keep iterating for a while, the thing blows up. But I'm just predicting 1 delta t into the future. So it never goes bad in 1 delta t. It's always over thousands of iterations, this thing will go to infinity. But if you're just going one, big deal. And this just gives me a rough idea of what the future looks like. Okay? Are there robots? Cars float? Stuff like that. Once you get that future prediction, then you can correct it. You can say, okay, I know what it is. I know that this scheme over here is much more accurate. But it relies on the future points. But instead of putting the future points, why don't I just put in my predicted future point? So it's a two-step process. So you say, okay, my actual future point is going to be the following. The way you're going to do this, somehow you're going to say, okay, let's take this kind of scheme again and say, my future point is the current point, but I'm actually going to use a weighted average between the current and the future point plus and then for the derivative term, which is supposed to be just using the future points, I'm just going to use the predicted future points. So somehow what I've done is I've averaged in my current point with my future point, kind of get a weighted average. And for my future point, or for this point, which are supposed to be future points, I'm just going to use a predicted value for the future point. So it's a two-step algorithm, two-step iteration. First, predict what this thing is. Use your prediction to actually use, this is the implicit scheme right here. but without having to solve an AX equal to B. So the idea is you're kind of using some implicit ideas with your standard just iteration ideas. And the hope is that this gives you improved accuracy. And it typically does. These predictor-corrector methods tend to give you really nice stability properties at a very low cost. Okay? Doing 2 iteration schemes is a lot faster than doing iteration order n squared operation. Iteration order n squared operation. This is really slow. Here, it's 2 iteration procedures, and that usually saves you a lot of time, and it gives you really good stability properties. Okay? All right. When we come back on Monday, what we're going to talk about is then how do you actually talk about the stability of these schemes? Because so far I've talked a lot about these things are stable or unstable. We'll talk about methods for actually characterizing instability on Monday, and on Wednesday I'll bring the laptop in and we will show you what happens when you violate these things and code blows up.